Okay, let's quickly talk about cycle time estimation. So before we do anything, I just want to emphasize on one of the words I used, cycle time estimation. So we're not trying to fool anyone saying that we can guess the time like perfectly. We do I think, a very good job in specific situations. So you need to be able to take advantage of those good estimations and understand when those estimations reach their limits. So I'm gonna have to move myself to, oops, not that here. Move myself to, why can't I grab my, can't, okay, grab myself this time. Perfect. I'm gonna move myself to the other side because cycle time analysis occurs on that side of the screen. So I'm just gonna make sure that I have here -1. I'm gonna go for something very low here so that we can really see the result of what I'm gonna do. So like that. So we have 50, 150, 50, 150, and -1 here. So everything is equal everywhere. I'm gonna make that all joint motion like that. If I run this one, pick place, run it, and let it run. At the end of the path, it will tell me how long it took. So 18.9 seconds. Important thing here. So this value includes all of the yellow path. So the yellow path will start from the starting point. So it will include certain points. So here this time it will take 18.7 seconds. Be aware though that if you have any, so if you use the same speed all along, the value that will appear here right at the start will be good. If you have speed change throughout the program, you need to wait for the program to be to end to know the exact value here. Doesn't matter if you are in 1x or 100x, so you can just press here for fast simulation speed and run it and have the right result. That would also work, but you need to run it, run the whole program if you want to have a complete, let's say, or relevant answer. So yeah, that's important to understand that the first point counts. So if you're very far away, you may end up having a longer path, so 19.6, because there was a longer run to reach that first point. So if you really want to have the path from where you start towards where you end, you just need to make sure to reach the first point before starting it, and now you can see it's 17 seconds. So if I stop that, go parameters, I'm just going to go to the first point, go parameters, and then, oops, increase that to 200, so 4 times faster. And now I run it, I was at 17, now I'm at 15.4. So it's not a huge gain. There's a gain here, but even if I multiply it by 4, the actual maximum speed, we're not having that much of a gain, because most likely our acceleration is not fast enough. It's just 150 degrees per second square. That means that if it takes more than 2 seconds to go from this point to that point, we won't ever reach the full potential, because like we have 1 second, a bit more than 1 second to go up to 200, because it's like 1 second plus 1/3, so 1.3 seconds to go up, 1.2 seconds to go down. So that means that we have 2.66667 seconds to do acceleration and deceleration. If that path takes more than that, that means that we won't ever reach the maximum speed. That means that maximum speed don't affect us as much as acceleration in this case. So if I go ahead and increase acceleration to, I don't know, 500 instead, and now I go to the first point and run the first path, now it went down to 8.4. So now it went down from 17 with 50 and 150 speed acceleration to 8 by having 200 and 500. So that's a huge difference. If I go back to 50 and 150, click OK and just run it real quick. I'm gonna go to the first point, run it and press space to go to the end. So 17, if I go ahead and just change the speed here to, I don't know, 500 and 1,500, 1,500, and go to the first point here, then run it and press space to go to the end, it won't change because right now we just have joint motion, and that cycle time calculation with default parameters is only affect the related type of motion. So circular joint motion will be affected by joint speed, and linear motion will be affected by linear speed. If I was to bring all of that to linear and go to the first point and now run it, it takes, according to that, 11 seconds. So oftentimes it's a bit slower with linear motion than with joint motion, because you're kind of restraining what joints can move at what time and stuff like that. Okay, so that was the first thing. Then obviously cycle time will be affected by the fact that you are or you are not using the rounding. So if I go ahead here, we have this value 500, 1500 minus 1 gave us 11 seconds. If I go ahead and just enter 1 instead, just so that you recall, entering 1, 10, 100, whatever here won't change anything for the cycle time. It will be the same no matter what. If you run it now, it will consider that it takes 5.5 seconds to run it. So that's not very true because of what I explained here. And in this case here, on purpose, I did a lot of that. So point, another point here. As soon as you enter -1, RoboDK will think that there's no waiting in between points. So even if the point was like up and down, you absolutely need to stop at some point because you have inertia to kind of fight, and you're going in one direction, you want to go to the other direction. So at the end of the day, your velocity needs to go to 0. RoboDK won't consider that for now. So the point is that if you're doing just pick and place with fine motion everywhere, the cycle time estimation, according to my test, will give you a value good within 1% or so, 1 or 2% maximum. So that's very good. But if you're adding some blending, now RoboDK will be a bit, and oftentimes a lot, optimistic for paths like that. On the other end though, if you are running a path like the gear loop here, and this is running and this will be running, I'm gonna press here. It takes 24.1 seconds according to that here. That if you have, and the goal, if the goal is to have a smooth path and you're exporting from RoboDK with the rounding and running it with the rounding on RoboDK. So this is a path that you're really like following a high amount of points, and that you're not like turning corner very quickly. So there's no reason for the robot not to be able to keep a fair share of its velocity. In this case, the cycle time analysis or estimation should be very good too, like within 1 or 2% too. So you only need to be aware of that kind of, let's say, very sharp turn or move forward and let's say forward and backward motion, where RoboDK won't be able to calculate stuff properly in this case here. So we will work on that in the future, but for now, just be aware of that situation. Another thing, if you add pauses like this one here, if you add pauses to your program, those will be included in the cycle time calculation or estimation. So I often add those if I have like to pick an object with a vacuum gripper and I know that I'll have to wait 0.25 seconds, let's say, for the vacuum to build up or to the vacuum to be released when it's time to release the box or whatever I'm picking. I'm gonna add those to my simulation so that they are calculated. If my gripper takes half a second to close, I need to do that. I need to add that. I'm gonna add a pause to my program and make sure that this is considered in my cycle time estimation. Last thing, very important, you remember when we were talking about singularities that one of the reasons why the robot was actually slowing down is because two of the joints, or two more, or at least one or more joints, were reaching their maximum velocity. By default, RoboDK won't check if a joint velocity is reached when you're doing a linear move. It will only look at linear velocity for linear move and joint velocity for joint move. But that doesn't mean that because you're calling a joint a linear move, that you won't reach the limit of the joint velocity. So if you want to be able to check both at the same times, you go Tools, Options, and then Motions, Move Time Calculation, and you use the strictest constraint. So by doing so, if you go to parameters, let's say if I run that, okay, I'm not gonna run this one here, I'm gonna run the other one here. So if I go to the first spot, oops. If I go to the first spot, I'm gonna increase that to 500, let's say. So if I do that here, click OK and run, it will give me a cycle time, I think 11.6. We'll see how it goes at the end. So we have 11.6. Oh no, sorry, I did change that. I didn't want it to change that first. Sorry, my bad. Tools, Option, Motion. We want to have, okay, I'm gonna go first with linear for move L and joint for move J, which is our base reference. So if I run that here this way, you will have 5.5, and you can see that there's no slowdown along the path. Like the path is always consistent. But we know that here from the move J, that in this section here, it's hard to keep the velocity because we're limited by the speed of joint 1, and that we're not that far away from ourselves, so that we won't have as much speed. But if we go to Tools and then Options and then Motion, and we enter strictest constraint, we go from 5.5, gonna go to the first position, to now having 11.6, and you will see the slowdown in this part here where we're limited by joint 1, and things slow down quite a bit because here we're limited by one joint. If we were to go ahead and increase the joint speed to, I don't know, 3 times the speed, and let's say go 3 times the acceleration, we are still having just linear joint here, so that with the default parameters that wouldn't change anything. But now if I run that here, we now have 5.6, so we're just 0.1 second slower than if we had no joint limit whatsoever. So that means that we're like, with those value here, we are very close to not be limited at all to reach those linear speed and acceleration. So I hope it was clear. This is, I think, an important feature with RoboDK, be able to estimate the cycle time, the time it would take to do a given task. So I hope you appreciate this introduction to that. I would highly recommend you to play with it. And as you can see, it's kind of a relatively picky feature. So you really need to make sure to have set your acceleration, your speed, your rounding properly before trying to extrapolate any information from there. And for now, I'm gonna go back and put that back to linear for move L and joint for move J. I always keep it that way when I'm not calculating cycle time because it just makes more fluid simulations. So I prefer it that way, but you can do as you wish. And I would generally, when I import a new robot, I would actually just take 2 seconds, go to parameters and make sure that the values here make sense. Those values, by the way, you need to make sure that it makes sense for your robot. RoboDK do not limits you. We said we support robots that are like 1 feet tall up to like 4 meters tall. Sorry. So we can't really know ahead of time what are the limitations. So in this case, you need to set your limitation according to the documentation or the information you can take for from your robot representative. So that's it for this. In the next video, we'll talk quickly about reach study.